Video, we're going to continue looking at the different states of matter, but we're going to look at developing models to explain what happens to a material as you heat it and cool it, including dealing with the state changes that occur. So from the last video, I suggested some questions that you might have about this particular graph that we're looking at here. And we already looked at the process of evaporation and how it's different to boiling, but we didn't answer these two really important questions, and that's why doesn't temperature change when state is changing, and why is process D to E longer than B to C? So we're going to have a look at answering those questions, but before we can answer those, we need to develop our understanding of the states of matter a little bit more. So previously we looked at the different states of matter in terms of the speed, in terms of the separation, and in terms of the forces between the atoms. So now what we're going to do is we're going to expand that slightly and talk about the two forms of energy that the atoms have. Then, to be able to explain the link between temperature and kinetic energy, I'm going to introduce you to a new temperature scale called the Kelvin temperature scale, and we'll compare it to the Celsius one most of us use. And then what we're going to do is we're going to use that model or relationship between temperature and kinetic energy to explain what's happening when we heat a material and its temperature changes, and when we heat a material and its temperature doesn't change during a state change. Okay, so let's first look at those types of energy. So we saw from the previous video that there are forces that are attracting the atoms together. That's what keeps solids in a fixed shape or binds liquids together, that kind of thing. And this force is due to the charges in the atoms. So we say that they have a form of potential energy we call electric potential energy. Whenever two things are attracted to each other, they'll have some form of potential energy. So this specific type is the work done to separate charges. So if something has a bigger amount of electric potential energy, it means we've done more work to separate those two things. So this form of energy is really similar to another form of potential energy that you will already have come across, gravitational potential energy. So that is due to the gravitational force between two masses, and we know that if we increase the separation between the masses, i.e. so lift an object higher up, that we can increase its gravitational potential energy. So if we move two charges or two atoms away from each other, we increase the electric potential energy. So it works in a very similar way. Okay, so let's actually look at our three states of matter and describe them in terms of their energy. So on the top left, we can see solids. So we know the speed of movement in a solid is very small and that they're closely packed together. So in terms of energy, we describe that as low kinetic and low potential energy as well. So they're slow, which gives them low kinetic energy, and they're closely packed, which gives them low potential energy. In a gas, we know the particles are moving fast and have large separation. So they have high kinetic energy and high potential energy. And liquids will come somewhere in between the two, so they have sort of a middle amount of kinetic energy and a middle amount of potential energy. But that's how we would describe the three states of matter. Okay, so that finishes that first point. Let's now introduce the Kelvin temperature scale, which will help us explain the link between temperature and kinetic energy. So in most of Europe, Asia, pretty much everywhere in the world, we use the Celsius scale of temperature. So for instance, room temperature very typically is about 20 degrees Celsius. Obviously in different countries, the outside temperature varies quite a bit. But unless you're an American or some places in Central America, you will use the Celsius scale for measuring temperature. And that scale is constructed from two key temperatures. So the one fixed thing is the freezing point of water, which is 0 degrees Celsius. And the other fixed temperature is the boiling point, which is 100 degrees Celsius. So every single thermometer that exists in the world is programmed or developed using these two fixed temperatures, and then they essentially divided that difference in temperature into 100 divisions, or 100 degrees is sometimes known, to give us our temperature scale. So that's how we can actually build thermometers using those two fixed temperatures. But in thermal physics, to help us understand what's going on with atoms, we actually use a different scale. We use a Kelvin scale of temperature, named after Lord Kelvin, who did a large amount of work in thermodynamics. So it's really easy to convert between Celsius and Kelvin. All you have to do is add 273 to the Celsius value, and you have the temperature in Kelvin, and the degrees in both scales are exactly the same size, so we don't have to worry about that. But there's only one fixed temperature in the Kelvin scale, and that is at what we call absolute zero, or the minimum possible temperature achievable. And it is not possible in the current models to go below this temperature, that is the fixed point. Have a look at some examples. So we saw on the previous slide how to go from Celsius to Kelvin. If we want to go from Kelvin to Celsius, we just need to reverse the process essentially. But 1 degree Kelvin is the same size as 1 degree Celsius, which is useful when we're converting them. So to give you some reference points, 0 Kelvin is minus 273 degrees Celsius. The melting point of water we should know is 0 degrees Celsius, so that would be 273 Kelvin. And the boiling point of water being 100 degrees Celsius is 373 degrees Kelvin there. But the reason we haven't used this new temperature scale is the relationship between atom kinetic energy and temperature if we are using this particular scale, and I'll talk about that a bit more in a second. So we've got our scale. Let's now have a look at that relationship. So if we plotted a graph of temperature against the average kinetic energy of atoms, we would find it's a straight line through the origin, which means the relationship is directly proportional to temperature if it's measured in Kelvin. So whenever you're reading about this or doing some research, you will see the word average everywhere. So I talked about in the last video how evaporation works because some atoms have higher kinetic energy than others, but what you find is that a certain temperature, the average kinetic energy is the same for all materials. So that's why you see the word average. And the useful thing about a directly proportional relationship is it allows you to describe very easily what's going to happen. So if we double the temperature, that would mean the average kinetic energy of a material will double as well. So that's why it's a useful relationship. Okay, so let's start thinking back to this graph that we've been using to describe what happens to water if we supply a steady rate of thermal energy to it. So we'll first look at these sections in red, the increasing temperature sections. As we just saw, if the temperature is changing, we know that means the kinetic energy of atoms is changing as well. So in terms of describing the energy transfer occurring, if we're heating something, we're taking thermal energy from the surroundings, often in the form of a heater or something like that, and we're converting it into kinetic energy of the atoms. If we're cooling something, that means we're taking some of the kinetic energy that atoms have and we're sending it out to the surroundings as thermal energy, and there's a few different processes for doing that, which I'll look at in a later video. So if we're supplying thermal energy at a steady rate, using conservation of energy, that means the average kinetic energy should increase at a steady rate also, which, based on the relationship we've just seen, means temperature should increase at a steady rate as well. So if we go back to the graph, we can see that in those three sections there, that it's a straight line graph, which means the rate of change of temperature is indeed constant if we supply energy at a steady rate. So we can see the graph matches up well with what that theory says. So let's have a look at this mathematically so we can actually model it and calculate some different things. So what we've just seen is if we supply energy at a steady rate, and I'm going to call the rate of which thermal energy is supplied delta Q over delta T, we saw it would be directly proportional to the rate of change of temperature, which I'm going to call delta T over delta time there. And we put in a K to represent what the gradient is, or the constant of proportionality. So if we use the same units of time on left and right, we can cancel those out. So we can see that the temperature change of material is directly proportional to the amount of thermal energy that we supply, which will be useful to us in doing some calculations. So we know that one of the things that affects essentially the size of the temperature change will be the amount of thermal energy supply. What else might affect it? Well, one of the things is the mass of a material. So if we have more material, the thermal energy is going to be shared between more atoms, so each one is going to get a smaller amount. So the average kinetic energy will not increase as much. So we know essentially that constant we had, part of it will be something to do with the mass. But that still does not fully describe what happens as thermal energy supplied. So we've developed this other concept called specific heat capacity to explain the differences we get between different materials. So what is specific heat capacity? Well, it's the amount of thermal energy we have to supply to change 1 kilogram of a material by 1 degree. And it doesn't matter if it's in Kelvin or Celsius, the degrees are the same size. So we can see if we make it the subject of the equation, and you'll notice most of the time we don't put a delta Q in the equation, we just put a Q for thermal energy supplied. We can see that specific heat capacity has the units joules per kilogram per Kelvin. So that matches up with the definition. Just a side note, if you ever see the word specific for some definition, it means per kilogram. So we know that's going to be part of it. So for example, the specific heat capacity of liquid water is 4,180, which means it takes just over 4 kilojoules of energy to change the temperature of water by 1 degree. So that is a pretty large amount of energy we're supplying. Okay, so this is how we deal with the parts of the graph where temperature is changing. We can model them using this equation here. The next question to ask is, well, how do we model those sections where the temperature isn't changing? And we're in a position to start answering these questions. So why doesn't temperature change during a state change? Well, the first thing to realize is if temperature is constant, that means the kinetic energy of the atoms is not changing. So if we're supplying energy, it must be being transferred into a different form. And it's the other form of energy we had to start with, it's being turned into potential energy. So as we heat a material, what's happening is the separation between the atoms is increasing, or we're doing work to separate the atoms instead of increasing their kinetic energy. Or if we're cooling a material, we are decreasing the separation of the atoms and getting work out to transfer to thermal energy to the surroundings there. So that's what's happening during a state change. So it's not kinetic energy that's changing, it's potential energy instead, which is why the temperature stays constant, because temperature is a measure of kinetic energy. So the next question was, well, why is this process D to E much longer than the B to C? And it is for all materials, it's not just water. So let's go back to our diagram states of matter. So we can see that going from a solid to a liquid, the change in separation is not that big. So that's a relatively small change in potential energy. Whereas if we go from a liquid to a gas, there is a big change in separation, so we get a big change in potential energy. So we've managed to clear up those questions. Let's now look at how we can mathematically model those sections of the graph too. So we have a slightly different equation to model this point. It's Q equals mL. So Q is still the thermal energy we're supplying or removing. M is still the mass of a material, but L stands for the specific latent heat of vaporization, or sometimes the specific latent heat of fusion. So just like before, the word specific means per kilogram. So the latent heat of fusion is the thermal energy to change the state of 1 kilogram of solid into a liquid, or the amount of thermal energy we'd have to remove to turn it from liquid into solid. The specific latent heat of vaporization is the thermal energy we have to supply to change liquid into gas. And again, it's 1 kilogram of liquid into gas, or the amount of energy we'd have to remove to turn a gas into a liquid. So just to look at it in terms of its units, just like we did before, if we make L the subject, we can see it has the unit of joules per kilogram. So there's no degrees or anything involved in this. It's just energy per kilogram. And some examples. So for water, specific latent heat of fusion is 3.34 times 10 to the 5, whereas the specific latent heat of vaporization is 2.23 times 10 to the 6. So you can see it's 10 times bigger for vaporization than for fusion, which matches up with what we saw before when we saw that we expect a much bigger change in potential energy from a liquid to a gas. So that is the method we use to model state changes as well. So that's where I'm going to leave off this video for today. In the next video, I'm going to look at some example calculations with these models we've just developed, so you can see how they're used. And we'll also, in a future video, have a look at how we can actually measure the specific heat capacity or the latent heat of fusion of a material as well. So that's where I'm going to leave it for today. If you have any questions, feel free to comment and ask. I will try and get back to you without those. But thank you for taking the time to watch.